All right, so welcome everyone to the second day of the symposium on the work of 2022 Fields Medalists. And it's our pleasure to have three speakers today. The first speaker is Subhajit Goswami, who will talk about the work of Hugo Duminil-Copin. Next speaker will be Piyush Srivastava, who will talk about the work of Junho. And then we'll take a short break. And then finally, Anish Ghosh will talk about the work of Maynard. Okay, so I think as more people are trickling in, but I think it's a good time to start.
Okay, thank you. Thanks to the organizers for giving me the invitation to talk here. It's a great pleasure for me to be able to talk on the work of Hugo. And probably unlike other talks, this talk would be a bit more personal, although I mostly talk about mathematics. But there will be some personal anecdotes, and it's because I worked with him. I mean, I've still been working with him, and I was his postdoc since after my PhD since 2017. And so let's see actually how it goes. Okay. Sorry, this seems to be the pointer. Oh, just hold on. No, but it's okay. No. Sorry for that. But it was working fine actually. No, that's working. But when you so shall I? Yeah, that I can do. So yeah. Okay, good. So here is a brief outline of the talk. I'll just spend some minutes about talking about the man, because he was, in my view, no less interesting than his mathematics. And I hope actually you'll enjoy that as well, especially also because there are many young people here, and there are several things about him which are quite inspiring to budding mathematicians. And then we come to the middle part of the talk, where we'll talk about a general overview of the mathematics, and in particular, a particular work. Yep. Okay, good. Thanks. And then, if time permits, probably I might share some anecdotes, which might be interesting and fun. Okay. So, there are many pictures of him available over the net. This one I took in particular, especially because he's talking about something. Yeah, there's a talk he's giving at IMPA, and he's talking about the work that I was involved in. And what is interesting is that, ever since I met him in 2017 for the first time, his hair he's very particular about. It just never goes down below this level, and he's very particular about it, as much as it's mathematics. So what's in? Okay, so let's take an overview of the guy, and you'll see why. Okay, so this is his trajectory before he entered research, and so he went to Louis-le-Grand in Paris. So those who know about the education system in France, so they have this three-tier system. So they have this. Am I audible properly? Okay. This grandes écoles like ENS and others, where actually there's extremely competitive schools, and where people take a preparatory class called Preparatoi for 2 years before for preparing for that. So he went to this school called Lycée Louis le Grand. It's a kind of very famous school because it was established, I guess, in the 17th century in Paris, and many people you know actually part of, many Nobel laureates and field medalists, include actually even before that, Galois, and in the Poincaré in the modern times, Laurent Laforgue, Alan Conce also, I guess, they all went to this school. So far he completed his master's from Paris Orsay at 2008 when he was like 23 years old. So far his trajectory was, like a very good student, very in any country. So, but nothing extraordinary about that. But something after that which I always like to showcase, and I like to look at what happened after that. So then he started to have wings, and you can see here within a course of 2 years he went from postdoc to the full professor at University of Geneva, and each of these years he published a major breakthrough. And he became finally the permanent professor at IHS at 2016. And it is also kind of corroborated by the list of prizes you have that he got. Many of the prizes we can recognize, and one of the things those who don't know, he got this Nobel Prize in 2017, one of the youngest person to win that. This is the highest award you get in the field of probability theory is given. By the way, I was just pulling this up from his CV when I realized that he hasn't updated it yet. Okay, good. Now let's come to the mathematics, cut to the chase. So this is his Fields Medal citation, solving long-standing problems in the probabilistic theory of phase transition, statistical physics, especially dimensions 3 and 4. And it's a very inappropriate citation because it's very difficult to list his major achievements, because it's so diverse and he has touched so many areas, different areas in this field. And in all of the things, in all of the works that he has done, a common theme is that there were problems that have been lying dormant for several years, several decades, and considered untractable. Okay, and after he set himself to this task, those things now have become commonplace. Okay, papers started to pour in larger numbers after he published some cornerstone work. So let's talk a bit then before I go to the second one. Let's talk a bit in general what we mean by phase transition. What is the mathematics of phase transition, as the title suggests. So phase transitions we all know, like we see it around us all the time, right? So this in physical phenomena, the solid becomes liquid, liquid becomes gas. So essentially the basic idea is that you have some kind of parameter like temperature, and you have something which defines the phase, okay, of the substance being talked about, and it changes in its macroscopic behavior as you increase it. Okay, and around a certain point, it abruptly changes from one phase to another. Okay, one of the particulars, one of the very popular model in phase transition that has attracted interest both from physicists and mathematicians, and for good reasons, and I'm going to explain why, is the so-called Ising model, where actually also, and models related to that, where actually the citation which this citation talks about, actually, whereas most of his groundbreaking contributions have been. So Ising model refers to a simple model for a particular phase transition called the ferromagnetic paramagnetic phase transition. So for that we have to go back to something like end of 19th century. So to a physicist known as Pierre Curie, you all know about, and he observed the phenomenon. Okay, so there are these materials like iron, nickels, and many things. So if you put it under a magnetic field, so put it near a magnet, it starts behaving like a magnet. Okay, and like this this magnetic properties arise, roughly speaking, kind of from the alignment of magnetic moments in the atoms. Okay. And what you observed, well, so you put this thing, let's say near a magnet, and it starts behaving like a magnet, and so this is called induced magnetism, and you slowly remove this magnet. Okay. Now you observe whether it retains this property or not. Now, what could you observe was that, well, there is a certain temperature called the Curie's temperature now, below which it retains its magnetization. Okay, and if you increase the temperature, if it is above that, okay, it loses the magnetization. It stops behaving like a magnet when you remove it. Now, then there are attempts among the physicists to somehow come up with a simple mathematical model which would capture this phenomenon. To this end, I think in 1919, there was the German physicist Wilhelm Lenz came up with a very simple model for this magnetization called the Ising. Okay, and why it is called Ising model, I'll come to that shortly. Ising was a student. He modeled it as follows. So imagine, let's say you're like a solid body. So you can imagine these atoms, or they are distributed, let's say, as in a lattice. Okay, we learned about lattice a lot actually in the last two talks, yesterday's talks, and take a very simple model. So okay, for magnetic moment, you just take, let's say, +1, -1, very simple, simplistic way. And what you do, so let's say, okay, so you have an assignment of +1 and -1 to every point in the lattice. Okay, and what you do is that you include an interaction term. So imagine they interact at short distance. So let's say two pairwise let's call them spins. They interact with each other. Okay, so this will talk to its neighbors, and the way it enters the picture, the model, is through a Hamiltonian. So it's like, I don't know if it's visible, but let's say this is formal, by the way, but let's say something like sum over sigma x, sigma y. X is, let's say, neighbor to y, belongs to the lattice that we're talking about. Okay, so remember the sigma x, they're just simple +/-. So what does this mean? Well, this roughly represents the probability that you'll see a configuration in an assignment of so the probability that you attach to a particular assignment of spins. Okay, and what is very clear, the first thing you should take from this is that, well, so the probability would be more if this thing is big, and it will be small if this thing is small. Well, when it is big, well, you can see that the biggest possible thing when basically this is, you can think of the energy is minimum when the spins, pairwise spin, the adjacent spins are all aligned. Okay, so that's a phenomenon when you see magnetic properties. Okay, usually, okay, so there is a temperature parameter which will reflect the thing, so that should add that. So beta is, you don't need to bother about that, but beta is which is called the inverse temperature. So this indicates the strength. Okay, this somehow it modulates actually to what extent this energy is to the effective behavior. Okay, so the ground state in a sense is that, well, everything will be aligned. Okay, and the opposite is completely chaotic state, disorder state. When, let's say, there are like +/-1 with no proper order, so the net magnetizations will be cancelled. If you have this, by the way, this is a formal, we have to make sense of things mathematically, because if you take it, sum it over infinite lattice, you get an infinite sum of + and -1, so that doesn't lead to anywhere. So you have to, there are much more modern mathematical machinery to talk about that, but let's not go in there immediately. So the question that actually you ask, so what is this quantity that we look at which captures this magnetization? So here one thing is that what is called the spontaneous magnetization. So remember, suppose that you have a finite, you fix a finite box and you take the average magnetizations restricted to this. Okay, you take the limit, but let's just focus on that. Okay, this is a quantity, and you can understand why. Because if this is a positive sign, you get, okay, in one direction you get a magnetization, or the other direction. Both will do. But if it is very small, essentially goes to 0, you don't have it. Okay, so what Lenz hoped is that, well, let's start with the simplest possible model and see. So remember here it's inverse temperature. So beta is big means high temperature, beta is small, okay, means beta is big means low temperature, beta is small means high temperature. Okay, so it's just the reversal, because inverse temperature is the way actually, this temperature, if you do the basic things in thermodynamics, you get what is the inverse temperature is the natural thing object to talk about rather than temperature. Anyways, so okay, and he asked his student, pays the student on easing, well, try to figure out whether there is, you can find a critical temp, locate from this model a beta c, okay, so that you can prove that, well, below which you will have a magnetization, okay, always, let's say with probability 1, and above which you will not see that. So what Ising did, he took the okay, in one dimension, that was his PhD thesis, and concluded, yeah, this model is a failure because there is no phase transition. By the way, nowadays actually, okay, I need the computation that's involved very explicit computation involving finding the partition function of this thing. But by the way, I think by the end of the talk, it should be clear that now actually you have much better tools. So let me just tell you as a kind of hint is that the reason why in one dimension you will not see any phase transition here is simply the fact that the connected intervals in real line are just very uninteresting. They are just intervals, okay? So in one dimension, you cannot observe any interesting phenomena because the collection of connected subsets of real line in one, they are not very interesting. They are very few, which is not the case as soon as you go to the 2-dimension and upwards. Okay, so he gave a negative result and he went into oblivion, and he had a very tragic life also in the hand of the Nazis, and it lay dormant for some years. Then in 1930s, Rudolf Peierls, okay, another well-known physicist, very well-known physicist, I think went on to win the Nobel Prize afterwards. He showed that, well, no, not so fast. You go to the 2-dimension and you see a critical temperature. There is phase transition. And then came a person called Lars V. Onsager, and it is called one of the canonical papers in mathematical physics that everybody should learn. I think by now probably that paper has like 20,000, I don't know, a crazy number of citations, one of the most cited paper. So using algebraic methods. Okay, so after you learn that, well, there is phase transition, now you want to learn where the critical point is. At critical point, as I'll explain, and which covers a large corpus of the work of Hugo Duminil-Copin, things become extremely interesting. Okay, so now actually the question is, where does this phase transition occur? Okay, at which point? And so Onsager used very algebraic techniques to compute the partition function, from which partition functions, remember, like in a sense, it's like okay, the sum of this. You can think of it as like a generating functions of this. Okay, and this technique was later formalized not long after Ising-Clifford algebra. You can actually explicitly compute those critical points. Okay, okay, and then it took off. It became the laboratory for the development of many techniques in mathematical physics and mathematics alike. Of no less interest is what happens at critical point itself, because that's very mysterious, because critical point is defined, as I'm going to explain to you shortly, with the help of a very simple model, which is nevertheless extremely mathematically rich. Is that critical point, you have a description which is like, okay, after this something stops happening or something. This is not enough. If you see, this is gives you very little to say more about it. But what is soon realized at the critical point, what you can take, so it is a very interesting phenomenon in physics that, well, you see, you start from at the macroscopically, they interact in certain way, and then these lattices have certain symmetries, but essentially finite groups of symmetries. But when you take look at it macroscopically, so let's say in a particular domain, you take small and small mesh and look at this by a process called scaling limit. They start exhibiting symmetries, okay, that would which are much rich, like conformal symmetries. Okay, they give rise to conformal field theories. And it is one of the very big mysteries that how actually you can explain this mathematically, that that this symmetries which are absent at the microscopic level, you gain it at the when you look at it macroscopic level. And it was solved again in the line of works where Hugo was also born mathematically. Okay, so that's one. Second thing is that, well, Onsager's proof was very nice, and but the thing is that it's not very robust. If you even go up, let's say 30 dimension, which is very interesting, of course, probably the most interesting, those performing those algebraic tricks, algebraic miracles becomes almost impossible, very difficult. I mean, let me put it this way. Also, let's say in several cases, whether these things, some phenomenon shouldn't be very sensitive to changing the microscopic details of the models. Okay. So if you have methods based on exact computations, they're bound to, they cannot explain this phenomenon. You need more robust techniques in order to escape why, for a wide class of models, no matter how you change them in the microscopic level, you get the same answer, same kind of quantitative and much more finer properties in the macroscopic scale. So I think from after several decades, people started to realize that, well, okay, so the fundamental quantities that you look at usually in any kind of this theories is correlation functions. Okay, make any meaning of that. In this case, you can say that, well, what is the correlation or endpoint? Take endpoints. What is the correlation between those spins? Okay, how they interact roughly. I mean, they have many interesting properties. For example, certain correlation functions have to be positive. So positivity problem, all these things. You can actually find it out. By the way, just for the mathematicians, Pierre Cartier solved one of this positivity problem. His famous algebraic geometer in 1970s from Ising, and he told me that, and nice story. Okay, but all of these things seem based on like, well, something miracle that you can perform. But then actually especially from late 70s or 80s, people started to realize that, all these things can be very well studied. So all these things, correlation functions and all these things, admit of what is called a graphical representations. What is this in modern terms? It's basically a probability distribution on graphs or random graph, probability distribution on infinite graphs. Okay. And there are precise ways in which, by a probabilistic device called coupling, in which you can transform the questions about correlation functions into geometric questions involving these large random graphs. Okay. Once this came, people realized it started a new flow of activities. People started to prove these results in great generality. And this is this line of work in which Hugo set his foot. Okay. So one of the class of very good this random graph models are so-called percolation models. Okay. Not all, but it forms a very big class, and where actually which field and Hugo kind of revolutionized. So here, then actually let's interject this comment by Wendelin, and is that said that everything is easier, streamlined, the results are stronger, the whole understanding of this physical phenomena has been transformed. Basically, half of the main open questions were solved by Hugo, and even not just solved. That, as I was saying, it made possible to answer some questions that had been laying, that people thought untractable even a few years ago. Okay, so let me start with a very simple percolation model. Okay, and I'll just try to illustrate to you how such a simple model also exhibit very vast complexity if you just up your ante a little bit. Okay, so here we go. So I'll take off the this is not the kind of, okay, now percolation theory is extremely advanced. You can talk about a wide range of things, and they appear in many problems in random algebraic geometry and other branches of probability theory, and they have in connection with nodal domains, many cases, but this is a very simplest model that you can start with, which already exhibits this phenomenon of phase transition, very simple way, even simpler than Ising model, arguably. Okay, so here we go. So on the left, you have, let's say, your favorite, the simplest, let's say, a two-dimensional. Why I'm starting with 2 dimension to be clear soon. It is not unrelated to what I said there, that in 1 dimension you don't see much interesting things. Okay, so you have this grid graph lattice, right, Z2, and let's say it could be also be tree and anything in between, which will be important in the talk. So it's connected. Okay, so infinite connected graph. Let's say the lattice square lattice Z2 or a tree, and what you do this simple experiment. So choose a parameter P, which is called the density, which will reflect the density of certain chosen vertices or edges. So there are 2 versions, 2 ways to do it. What you can do? Well, you just go and every vertex and just decide whether to keep it in your graph or not, independently with probability P. Okay, same here. So at the end of this experiment, what you get? A subset, a random subset, okay, of your underlying graph, and the graph induced by the subgraph induced by that. Okay, so that's your outcome of your experiment. So this is side percolation. You can alternatively do it also with bonds. Actually, you can remove the bonds with some probabilities from the graph. Similarly, get this thing. So what does it give actually? So I'll talk about the mathematical representation soon. So let's say this picture, which reflects. Okay, so remember, P is kind of the density with which we are keeping the sites or bonds as they may be. So of course, you can expect as P increases, this thing should look more cluttered, more blackish. Okay, so this point and this point, this is like whitish, this is blackish, and this is near the critical point where interesting things start to happen. Essentially, well, this is probably not very evident here. If you look at the boundary curves of these black regions or the white regions, you will see random fractal curves that are conformally invariant, which forms kind of the backbone of like the late 21st, okay, the early 21st century probability, the Sham-Leuven revolution. Okay, so we'll not talk about that today, but that's also okay. So let's talk about the mathematical representation. So what I just said, well, what you can do is that you can encode this configuration by assigning a number between 0 and 1 to every vertex of your background graph. So 1 if it is open, 0 if it is closed. Okay. So what we are getting is basically a probability. So it is a product space, if you took, and so it gives you a probability measure on the space of random subgraphs of the background graph, where the probability measure is simply the product of like P if it is 1 minus P if it is 0. Okay, as simple as that. Good. So what is the very basic event that we want to look at here? Well, the background graph was infinite connected graph. What we want to first look at, and some extension of that already explains these functions that I was talking about. Okay, probably I might not go to, but make some allusion. Whether 2 sets, let's say large sets or 2 sets, are connected by an open path. Okay, that's the question. Because you see, initially, of course, everything was connected because I started off with a connected graph, and after the experiment, okay, I create some holes here and there. And I want to know, well, whether 2 sets are connected using a path which is all black. Okay, in this case, open. Is the setup clear? Okay, as simple as that. It's nothing much. Okay, so let's look at the probability of this picture appearing. So what is this probability? Well, this picture saying is that, okay, let's take any point X. You can take it with the origin of your lattice. And you ask whether you can connect, you can go to a large surface, okay, through an open path. Okay, that's the event. Okay, you have to connect it to a large distance. Well, a simple thought actually just revealed to you. This is decreasing because it becomes more and more difficult as you increase the distance, right? And it goes to this function, which is whether X is connected to infinity. okay, where the X lies in an infinite connected component of this random subgraph that you curved out. This is basically the analog, and this is I'm not saying like a superficial analog. There is a device called Edwards-Sokal coupling, by which this is exactly for not this percolation model, for a different dependent more complicated percolation model. This is basically the spontaneous magnetization. What is the quantity that we are looking at? Okay, so in order to study the phase transition, you can instead study like how this changes, this behavior changes when you increase or decrease. Or P is basically, think of it like the temperature. Okay, so now let's see. Okay, so what's the big deal about it? Everything is so well stated, everything is product. You can just write down explicit formulas. So well, then now why don't we just write it? Okay, so theta n xp is just the sum of all configurations, right? There's just basic additivity of measures, and you just sum over all configurations in which you see a path, open path between 0 and the boundary. That's simple. Okay, so let's see what is the configuration of probability. That is also simple, just like here, not unlike there. A particular configuration, if you just write it down, is just a simple, nice exponential function. Okay, and exactly same. It is also an exponential function. Actually, there is a kind of parametration so that something like that can be represented like this. So I'm just multiplying p whenever I'm seeing 1. So remember, omega y is 1 or 0, and otherwise I'm just putting 1 minus p because my measure was a product measure. That's easy. Well, what is the difficult part? Okay, now let's do the next step. Evaluate the sum over all admissible configurations. There you get stuck. This is basically, sorry. Oh, okay. Essentially, the problem is that of computing the partition functions in physics, statistical physics. Okay, and as I told that this analogy is not artificial. This is a mathematical statement. Okay, okay. So now let's look at the very basic questions about this. So now actually decided probably the going about like doing exact thing might not be that useful. Let's study some basic course properties that anybody can say, like even beginning undergraduate student can see. Well, one thing is that this function as a function of p is non-decreasing. Okay, so it can be this, this, or this, because well, p represents the density of open vertices. If p is 0 at one end, of course nothing is open, so probability would be 0. If it is 1, everything is open, everything is there, and the graph is connected, so it's 1, and in between it's increasing. By the way, if it is, try to prove that it's non-decreasing. Okay, it's easy. It's just one sentence proof, but if you're saying it the first time, it will not be immediate. That might be a nice take-home exercise, but anyways, but we can believe that very well. So these are many of the ways it can happen. So let's see. Okay, and from this monotonicity, we can already locate a critical parameter where the first density kind of where it stops becoming 0. Okay. Okay. By the way, I didn't say. By the way, this doesn't solve this. Let's say the Ising's PhD question. By the way, that whether this is non-trivial, because PC could be 0 or 1, and then that would be like having no phase transition. Okay, I'm not saying that PC cannot be 0 or 1. That is one of the questions that will devote the rest of the talk to mostly. But I can define it nevertheless. Okay, good. So, what are the bad situations? Like, it is not a good enough model of phase transition if either of these two happen. Well, from 0, and then actually you start seeing a positive probability, let's say. Okay, so this is this picture, first picture, no phase transition. Okay, it's always if you put any p and it becomes ordered in a sense. So you can think of like having large connected sets as if synonymous with having an order, large scale orders. Well, and the bottom case where you never see an order. Okay, you never see unconnected big connected sets, which is also uninteresting. Okay, no phase transition. The only case that is interesting is this, the one represented by blue curve, where okay, up to PC there is a certain point which is the PC. You stay 0 and then you start becoming 1. Okay, so first PC is always positive. That part is not very difficult if you have any any high it's a proof. Yeah, I have to wrap up. So it's 5 minutes. Okay, good. Then actually probably not good part. Okay, so this probability is very basic path counting arguments. At the level of high school, you can just do it. Okay. Now let's up the ante a bit. What happens? Okay, so this is one side. PC is positive, which is good. I mean, I said that, well, this picture is not happening. Now, what about this picture? Well, for that already, if you look at the particular example of a two-dimensional lattice, it's still classical. It's still classical, but you need to use a bit more advanced resultant topology called the Poincare duality to argue that. Okay. That so that actually shows that if you just up the ante a bit, it starts getting traction. Sorry. Okay. So now the question is that, well, now actually the mathematicians enter the picture and take it beyond any game. So like, well, nobody is preventing you from asking the same question on general graphs. What kind of graphs? Well, graphs that are very interesting are, let's say, the Kelly groups. Kelly graphs of finally generated groups. Okay, I don't have time to talk much about that, but these are the natural representations of finally generated groups that you can do. Okay, which somehow reflects the multiplication table of the groups. Okay, and for groups, if you want to do that, deriving a generic condition, pulling this topological trick, it becomes very, very, very difficult. So the guess was, and again, you can just think why one dimension you cannot have any phase transition is basically because it's very easy to disconnect a set. You just have to cut off 2 points. Okay, so that's not costly, and that's basically the reason why Ising also cannot have any phase transition in dimension 1. Okay, only when you go to other dimension you see non-trivial surfaces, and that's when that's where actually the richness sets in. So the conjecture was by Oded Schramm, one of the doyens of modern probability theory, and Itai Benjamini, conjecture that, well, you should have this non-triviality of phase transition whenever the graph satisfies, the graph is dimension is bigger than 1 in some suitable notion of dimension. Okay, because the notion of dimension for general such graphs may not be so clear. So previously people did, like, there were works from algebra, there were works from probability theory, whether they took any general class of groups, like say there are many interesting classes of groups, they took one type of groups and they proved it. So every type of groups that were presented, they could prove that PC is less than 1, several works, but no unified theme could be found. And then there was this work by Duminil-Copin, the man of the hour, his 2 PhD students from Israel and some random guy, who said that, well, it was settled that if it's bounded degree, which is a reasonable assumption, quasi-transitive, think of it as like the graph has only finitely many perspectives. More the automorphism group has only finitely many orbits. And with the superlinear growth, essentially it says that if you take balls in the graphs, there is a natural distance function that is associated with the graph. Its volume grows superlinearly. Then you can find the threshold is strictly less than 1. And what is a nice part, I'll just end with that probably, that the proof is that it combines areas which are kind of not foreseen for a long time. It uses a spectral, it combines the spectral properties of the graph, which is the spectrum of the discrete Laplacian that we can define of the graph, and to some process that analogous to denormalization in physics. What it does is that you can actually using this the spectrum, discrete spectrum, the discrete Laplacian on the graph. You can define a certain, you can introduce a certain structured population model, which is not independent, which goes to the contrary to this common intuition that if you have product measures, if you have independent tosses, things are easier. Okay, you actually do it on a dependent population model, where actually it's proving this kind of quantity seems easier. And then what you do is that you set up a deformation of this probability measure. So at one end you start with this nice one where you can say a lot of things, do a lot of exact computations. On the other hand, you have this independent population, and you, in the space of measures, in a sense, you create a smooth path in a way so that as you move along this path, the probability of seeing an infinite path always increases. So at the end of the game, you just conclude what you wanted for your models of interest. This technique has since been adopted in many other areas in probability theory and has given rise to very beautiful papers. Okay, so since I don't have very much time, so I'll probably stop unless somebody asks. So here, congratulations to Hugo again. So this is what we used to do while doing math. So yeah, thank you. Yeah.
Thank you, Subhajit. Yeah. Second.
At PC, you rule out a jump by these techniques.
Oh, that's a big question, right? So okay, so no, so this is called the continuity of phase transition. So if you want to have these things like field theories and scaling limits of the critical models, you have to have continuity of phase transition. So this is one of his principal citation, by the way. He proved, for example, the continuity of Ising in dimension 3 and many other models. In 2 dimension, it's continuous. In high dimension, it's not. One of the major open questions that is still lying there open is that whether in 3 dimension at PC you are not expected to see a jump. It's proven for Ising, by the way. Again, a thing. You see, Ising has dependence, but you can prove it. And but for percolation, which is the independent thing, the proof is still not known. It's one of the major open problems. Yeah, you don't expect a jump, but it's very difficult to prove it.
All right, maybe one more quick question if there are any.
Yeah.
Yeah.
Could you summarize what he proved about the Ising model, please?
Oh, okay, sure. So so he has many. Okay, so Ising he proved Ising and Potts many things. So one of the things is proven like so Michael Eisenman proved that the continuity of phase transition of the Ising model until dimension 4, and the dimension 3 proved particularly elusive for a long time. So one of his works was that to prove the continuity of phase transition, that the spontaneous magnetization is 0 at the critical temperature of the Ising model. And his recent work, which is actually also gotten cited, is that he proved dimension 4. It was conjectured that you cannot get any non-trivial field theories by taking, let's say, scaling limits of 5, 4. So from Ising and 5, 4, it's trivial. So you get a Gaussian field. So that's actually one of his recent major works. And so those two actually come to the fore. And for Potts model, general Q Potts model, there was this long-standing conjecture in dimension 2 that it should be continuous up to 2, 3, 4. 2 is Ising, 3, 4, and from 5 onwards it should be discontinuous. He proved both. These are some of the.
Slightly tight schedule. Not take more questions. We can ask questions. Show it later. Let's thank the speaker.
Thank you.
All right. So maybe without any break, let's introduce Piyush. Okay. So our next speaker is Piyush Srivastava, and yeah, talk about the work of Steve.
Okay. Thank you. Okay. So thanks for asking me to give this talk. So I'm going to. So it says selections, and I really mean selections. It will be a very small selection, and that will basically depend upon what I have tried to study in his work. Most of it will not be covered. So people who want to hear about Chow rings, I'm sorry, I won't be talking about Chow rings. We'll see what they are later, or we will not see what they are later on. But I'll talk about some other things. And so the first thing I'll talk about is the matrix. So this hopefully everyone has seen. So matrix, and I was just think of a matrix as a collection of columns. So n columns. The dimension doesn't matter for now, but there's a very natural notion of independence there. So some subset of columns is said to be independent if it's linearly independent. No non-trivial linear combination is 0. So then you can define these bases. And what are the bases? These are the maximal independent sets in a matrix. So this is standard thing. And one interesting property that we often take for granted that this set of bases has is the following: that if I take two different bases, two different sets of two different maximally linearly independent sets, then they have this exchange property. What is this exchange property? I take two of them. I take one element in one of the bases which is not in the other one. Then I can exchange it out. I can find another element in the other one, A2 in this B2, which is not in B1, so that I can remove this A1 from B1, add A2, and that will still be a basis. So this is a pretty trivial kind of property. We don't even think about it often when you're using it. So what's a matroid? So the name comes from Whitney. I learned recently that apparently at the same time in a completely different so Nakasawa also discovered the same notion around in the same year in sort of completely unrelated. So it's pretty amazing. And the name commutual geometries, apparently Gian Carlo ran some kind of what at least one person calls a campaign to rename matroids as geometries, and he's used words like grotesque and so on to describe the term matroid. But anyway, so what is a matroid? So you have a finite ground set, and there's a set of bases. So this is one way to define a matroid. I just define a set of bases, and the only thing I require on my set of bases is this exchange property. So there's a ground set. The bases are some subsets of the ground set, and they must have the exchange property, the same exchange property that we had for our basis sets for columns of a matrix. Okay, so this so far is it looks like what has happened. So already, if you think for a little bit, this already implies that all the bases must be of the same size. This is again something we know in a vector space. There are many ways to prove it. Here, just this is needed, and this is enough to prove that. So all bases must be of the same size. And now you can define independent sets. So what are independent sets? They are just subsets of bases. That's our notion of independent sets. And rank is defined for the matroid to be the size of any base, which are all the same as a set. And the rank of any set is defined to be the largest size or largest independent set that is contained inside. So this is what a matroid is. So any questions about the definition of a matroid? Oh, so some set, so some finite set, some arbitrary finite set, and then I take some subsets of some collection of subsets. They are called a set of bases if they follow this exchange property. That property already implies that they must all be the same size, and that's my matroid. That's it. Okay, so what are examples of matroids? So the simplest example is the one I already told you, the linear matroid. So the linear matroid is just a collection of columns. So you just take any matrix and just take the set of bases, like the basis of the column span of the matrix. That's sorry. Sorry, what? No. So so you only take the bases that are subsets. I mean, you only take those bases that that are subsets of the columns, not all the bases. Still finite.
So the ground.
Yeah, so ground set is just the set of columns of the matrix.
Oh,
it's finite. Just n. Yeah. Okay. So this is a linear matroid. And in fact, so let me say something. So here's another matroid called the graphic matroid, and maybe now some commentaries comes in. So what's the graphic matroid? So now my ground set comes from a graph. So there's an undirected finite graph with vertices and edges, and my ground sets are the edges. So ground sets are not the vertices, the edges, and the bases are those subsets of edges. Which, if I just put only those subsets in the graph, then the graph I get has no cycles. So here is an example graph. Here is an example of a maximal base of the graphic matrix of the graph. Here is an example of an independent set that is not a base. Okay, it's one small. So the bases in this case will be the so-called spanning trees. They will be of size exactly n-1 if the graph is connected. N is the number of vertices, and all the spanning forests will be independent sets. Actually, I'm cheating a bit. This is also a linear matroid. So there is a whole theory of representable matroids, which are the matroids that can be written as linear matroids. There exist matroids that are not linear, very small ones, and so on. Those questions I'm not going to go into, but this is just one example. Okay, so we have seen this. Okay, so we want to go. So this is all cometrics. Now we want to get into a somewhat different flavor. So one thing you can do with a matroid is write down this polynomial, which is something you'd always do in combinatorics. You have an object, you try to write down some polynomial that describes its properties, and the obvious one here is the basis generating polynomial. So what is this? You have one variable per element in omega, and then for each basis you have a monomial, which is just the product of the variables that belong in the basis. Okay, so it's the number of terms is equal to the number of bases, and the degree is equal to the rank. Okay, so what is this? Here's one special case. The special case is for the graphic matrix. It's the so-called spanning tree polynomial. The spanning tree polynomial is just so now you will go over the spanning trees of the graph, and the product will be the variables for the edges which are in this tree. So this is just the special case of this. And here is again we probably use the first sort of slightly non-trivial result, although it's classical. And the proof is quite similar to Kirchhoff's matrix tree theorem, if you know what that is. But what it says is that it's something that's not obvious in the beginning at all, right? So it says that this polynomial, if you put in variables here which are all in the upper half plane, all have positive, strictly positive imaginary part, then this polynomial will not vanish. Okay, so already some geometry has been brought in, and so this is again I couldn't even find a reference as to when it was proved, but yeah, if you use the Kirchhoff's matrix theorem, it's not so hard. So it's easy to believe it's a classical. Okay, so this is something we know. And here is something interesting. So this is a result from 2004. It says that if a homogeneous multilinear polynomial with non-negative coefficients has this property, this upper half plane stability property, that it does not vanish if you put all the variables. I mean, they're not all equal, but all the variables are assigned values in the upper half plane. If the polynomial never vanishes with any such assignment, then it's the support set. So the set where it has non-zero coefficients, that set must form a matroid. Okay. It's not an if and only if condition. There are matroids for which the generating polynomial is not upper half plane stable. So upper half plane stable is also called real stability. So I'll sometimes use that if I don't remember that I'm not supposed to use it. But yeah, so real stability, upper half plane stability is the same object. And there are matroids for which the generating polynomial is not upper half plane stable. And the spanning tree, the sort of the simplest sort of interesting matroid we can think of, that polynomial though is okay. So one question that already arises is, what is then a precise geometric characterization for matroid? Is there some such characterization of this form? But that's not the only thing. Here is something else. This again probably not immediately sort of even apparent that this kind of thing should happen. That's a property of upper half plane stable polynomials. Is that if you have a probability distribution and if its generating function has this upper half plane stability property, then the probability distribution has something called negative association. So it's very strong. It's a strong form of negative correlation. So it says that if A and B are disjoint sets of, so this, for example, I'm just writing it here for the spanning tree polynomial. So the spanning tree polynomial has the upper half plane stability. From that, it follows that if A and B are disjoint subsets of the edges, and you sample a uniformly random spanning tree, then the probability of both A and B falling inside that is less than the product of the probability. So it's negatively. So any two such events are negatively correlated. Okay. So this follows from this sort of. Like, yeah, you have to do some work, but this is a generic property of our upper half plane stable polynomial. Okay, so then the question I asked, maybe if we could get some geometric characterization for matroids, then maybe we could get some similar correlation inequalities for general matroids as well. And one conjecture in this setting, for example, which is still a conjecture, was suppose I just put S and T equal to 1, so just edges or just elements. And if we just choose uniformly random spanning forest instead of spanning trees, so not just at the top layer, but all the layers in the matrix, does that have this kind of negative correlation? That is still open. Okay, so far I've just been talking about questions. So here is one of the contributions that's also listed in the citation comes in. So this is this notion of Lorenzian polynomials. Actually, the definition turns out in part of the result that they had is that the definition actually had been found before in another form. So a Lorenzian polynomial is the following. So homogeneous polynomial with positive coefficient. So this is the setting we have been working with so far. It's called strictly Lorenzian if it has the following property. If you take the polynomial and apply any number of derivatives to it, just derivatives of the variable, until it hits a degree 2. So you have to apply, so if the degree is D, you have to apply D such derivatives. You can apply the same derivative multiple times also, that's allowed. Whenever you get to degree 2, you get a quadratic polynomial that quadratic polynomial has a Hessian. That Hessian should have a Lorenzian signature. So that's where the name Lorenzian comes from. So it should have exactly one positive eigenvalue. So every other eigenvalue should be 0 or below. So those polynomials are called Lorenzian, strictly Lorenzian, and Lorenzian polynomials are just limits of these polynomials. So that's what a Lorenzian polynomial is. So right now it might look like a strange kind of a definition. Just bear with me for a while. It turns out that Gurwitz in 2010 so this paper came, so 2020 is not the real date. The real date is probably more like 2018-19. So around 8 years before that, Gurwitz, in some slightly different context, actually in a similar context of trying to understand discrete notions of convexity, had this definition that a homogeneous polynomial is non-negative quotient called strongly log concave, SLC, if the logarithms of the polynomial and all its derivatives. So the polynomial, so you take the polynomial, take its logarithm, that should be concave, that logarithm function should be concave. And this property should hold for all derivatives of the polynomial also, all the way down. So if that happens, that's called strongly log concave. These two were shown to be equivalent. So this Anari, Garan, and Vincent also at the same time. I will talk more about this series of works. So they came up with something called completely log concave polynomials. That is also somewhat similar. So all these three turn out to be equivalent for homogeneous polynomials. So we'll just look at one. And here is sort of the main result for the matroid setting. So the full power of it, I think, is only in this paper, but quite a bit of the ideas were also, so around the same time discovered by both groups, is that a homogeneous multilinear polynomial with all positive coefficients equal to 1. So that's again the set we were working in, is Lorenzian if and only if it's the basis generating polynomial of a matroid. So now we have found that geometric characterization. So it's a characterization in terms of some properties of geometric properties of certain polynomials, and it's an if and only if characterization. Okay. And one thing, so I mentioned correlation inequality. So does this give a correlation inequalities? No, it's not as strong. So so another result in the same series of works is that all upper half plane stable polynomials are also Lorenzian. So it's a strictly larger class. And so far, all that is known, again from the same result and slightly earlier work of Schroeter and Wang, is that it's not so you don't really have this full, so you'd want this number to be 1 here for full negative correlation. The number is 2 minus 1 over the rank, so it's about 2. The conjecture is that it should go to 8 by 7. 8 by 7 is the best. Below that, there are counterexamples. But the point is that the conjecture is that this could be replaced by 8 by 7. So one more thing I want to say, that the Lorenzian polynomial thing, so far I've been talking about homogeneous multilinear, it extends to non-multilinear also, but that requires a generalization of matroids to multisets known as M convexity. So any questions at this point? The one, yeah, so you just remove this and that's it. Yep. Yeah, so FKG is, so it's like, it's the input or output of FKG depending on how it, yeah. Oh yeah, FKG is positive correlation, yeah, but this is negative. So negative is okay. So negative correlation is somewhat more interesting for algorithmic purposes because it usually implies concentration. Positive correlation is the opposite of that. So that's the problem. Yeah, and so for forest like things, because you will expect this, but even for forests, yes, you can prove it for trees, but not for. Yeah, so okay. So I think they have it. I don't have it. Yeah. So they let me just. So, but below 8 by 7, there are counterexamples, like explicit counter. Okay, so every talk should have a proof. So I'll give a proof. It's a tau proof. So I'll just prove one side of the sort of maybe the hard side or whatever, or the interesting side in some sense of the theorem for the case of matroids of rank 2. So this actually is an important step in the proof, although it is quite elementary, but once you have this, actually the rest is quite abstract sort of thing to build it up. But let's just do this calculation. So what we want to show is the basis generating polynomial for matroid of rank 2 is Lorenzian. Okay, so matroid of rank 2, so all bases have just 2 elements. Okay. So let's do this. And so the question is, why should matroids have anything to do with Lorenzian things at all? Okay, So omega is our ground set, B is a set of bases, this script B, and all the bases are of size 2. Okay? So that's our. Okay, so let's write down our basis generating polynomial. It's a quadratic polynomial. For every EF set in the base, you have XE times XF. So this is easy to see that you can write it as half X transpose X. It's like a bilinear form. It's a bilinear form of a symmetric matrix, and the symmetric matrix is what? So it's just 1 whenever E and F form a base, and it's 0 otherwise. That's it. So nothing has happened. Okay, so everything is fine so far. Okay. Okay, so and what is the Hessian of this polynomial then? The Hessian of this, once you have this form, it's pretty easy to see. The Hessian is just half of A. Right? So the Hessian is really essentially just A. So what we have to do is to show that this Hessian, because it's just degree 2, we cannot apply any derivatives. All we have to show is that the Hessian has this Lorentzian signature. Okay, so that's all we want to do now. Okay, and if we do that, the theorem would be proved. At least this toy case, which is actually an important special case of the theorem, will be proved. Okay. So now we have to understand what this matrix A looks like, and I've fully defined what this matrix A is. But let's again think a little bit about it. So the matrix A is, so it's 1 if the EF is a base, 0 otherwise. And here is where the matroid property comes in. And this is all these 2 lines are doing a lot of work. So if I have 2 elements A and B and another 2 elements C and D, they're all distinct. A, B, C, E are 4 distinct elements. If the AB entry of the matrix is 1 and the CE matrix of A is also 1, then I claim that at least one of AC and AB must also be 1. Why is that? Let's see. So A and B. Sorry?
You mean either AAC or AAE must be 1?
No, AC and AB. So I think that's the correct one. But let's do the proof and then we'll let's see.
AAE is already 1. We are replacing B with either C
Oh,
or E.
Sorry. Yeah, sorry, yeah, right. So CA or CB, one of CA or CB. Yeah. So AAB is a base and CE is a base. So here I take this one, I drop E, and now I must be able to replace one of these and get a base again. So either CA or CB must be there. Okay. So yeah, so sorry for so it's AC or CB. Let's okay. So just write it a different way. So in a different way, this means something like this: that if B belongs to some base, so here is B, and it has some other friend, which so that together with it lies in one base, and there is another AC, and suppose I know that B and A are not in a base, and B and C are also not in a base, then this edge, this cannot be there. So A and C also cannot be together in a base. This is just a contrapost. Okay. So what this is saying is that this is another. So usually, so if you read the paper, for example, they will say you just do the parallel classes. So what you can say is that when A and B are not in the same base, why are they not in the same base? Because they're parallel. Like in the graph terminology, that's very clear. So why will 2 edges why will you not be allowed to put 2 edges in a base? The only way that can happen is the graph is not simple and the 2 edges are parallel. Only then 2 edges can form a cycle. So, and once you say the word parallel, it sort of says, okay, if it's parallel, it must be an equivalence relation. And that's the proof that it is really, the word parallel makes sense in this case, because it is, that proof is that this thing is the equivalence relation. And so what we get out of this is that we can partition this omega into these classes, S0, S1, so on. S0 is special. S0 is those really bad elements which are not in any basis. So what does that mean in the graph setting? So these things are called loops in the matroid thing. And that's again because how can there be one guy will never be an independent set? That can only happen if it has a loop on itself. That's the only way there can be an edge loop. So you call them loops. So those are those guys. And there are S1, S2, ST, which are like these equivalence classes of things that are never together in a base. So this matrix A looks like this, that it is 0 if any one of these two is an S0, or if they are both in the same SI for I bigger than or equal to 1. Okay. Otherwise, it's 1. So at this point, I would just like to say that, yeah, it's done. So, but yeah, here is a picture. So that's maybe easier to see. So there's S0. So those blocks are all 0. And then in the lower blocks, you have 0 diagonal blocks, but all the other blocks are 1. So what this, so the upper block doesn't matter for the eigenvalues anyway, those only contribute zeros. In the lower block, it's like a all ones matrix minus a bunch of smaller all ones matrices in those blocks. So that's exactly what this representation is saying, but this representation is literally just a, I mean, it actually I wrote this incorrect. Actually this is not right, but from this you can the numbers are not right, but from this you can easily get that there's exactly one, that can be at most one positive eigenvalue, which is this one. If everything else must be negative or like not positive. So this basically gives you the full eigenvalue decomposition right away. Okay, so that's proof. In the remaining 10 minutes or so, let me again go back to the reporter mode, as Mohan likes to say. And so that was the only proof. And let's now see what other things are Lorentzians. There was mate, right? So what other things are Lorentzian? So here is another classical object called the volume polynomial. This is again something, at least the first time I saw it, it's just like it just looks like something that could not possibly be true, but then you think about it and it's like maybe it is true, and but yeah, still. So the point is the following, that if you have some n convex bodies in R to the D and you write down the volume of the Minkowski sum, weighted Minkowski sum of those, the W as a non-negative coefficients. So what's the Minkowski sum? So the Minkowski sum is exactly like the point in the Minkowski sum is obtained by taking sums of points in the original bodies, and the weighted things you just put the weights, and that's the definition. So the Minkowski sum of this guy and this guy is this. So something like that. So the volume of the Minkowski sum is given by it's a first the thing that is really miraculous is it's a polynomial of a certain degree, and the coefficients do not depend really upon the. I mean, there are some functionals which are the functional is the same, and you just put the ki's in there, and that's so these things are called the mixed volumes. So they have exactly n. So it's degree d and n. So there are exactly n arguments, and sorry, what was I saying? So there are d arguments because in R to the d. So it's and alpha is n tuples of. So it's like basically saying how many times each body is appearing in that term. So that's it. Such a polynomial exists, and it was already observed. So I'll say what this is. Already observed by Gurwitz in his paper on the strongly log concave polynomials, that these polynomials are strongly log concave, and hence by the equivalence that Brendan who established, they're also Lorentzian. Okay. And this happens to be a consequence of something called the Alexandro-Frenchel inequality. So what is that? So this is the following inequality, that this mixed volume, these coefficients that appear in the volume, the Steiner-Minkowski volume polynomial, they have this kind of a sort of like looks like a log concavity type property, which is the following, that if I take some, the notation should be C1 to CD. So if the volume, if I take the mixed volume of C1 to CD, and then square that, and then on this side, what I'm trying to do is to like make it somewhat more equal. So C1 and C2 are here. So here I just change one of the C2s to C1. So C1 gets repeated twice, and here C2 gets repeated twice. The other parts remain the same. So when you do these kind of sort of equalizing transforms, and then so that's the kind of concavity property, right? The equal thing sort of is lower. So that's convexity property. So that's the Alexandro-Frenchel inequality, and so volume polynomials are Lorentzian. Not all Lorentzian polynomials are volume polynomials. So why am I saying all this? The point is that Brendan and who also showed that although not all Lorentzian polynomials are volume polynomials, their coefficients do follow exactly this kind of inequality. So I won't write down the inequality, but exactly this kind of inequality, in the sense that if you take the volume polynomial, you use the fact that it is Lorentzian, you get back the Alexandro-Frenchel inequality. Although, I mean, it's not a proof of Alexandro-Frenchel inequality, because the proof that it's a Lorentzian polynomial itself uses the Alexandro-Frenchel inequality. But so that's pretty interesting. That so this is very much about volumes. The way even this formula is proved is via polytope approximation. I think that's the standard proof. So you approximate convex bodies by polytopes, and then get the polynomial, and then use a continuity argument. And here there is the completely discrete objects, but find this one of the main linchpins of that theory of volume polynomials. You get an analog here, right? Okay, so here's another success of this theory. So maybe a similar kind. So so again, let M be any matrix, and now look at something else. So now we look at this for each k. I look at independent sets of given sizes. So for each k, I look at independent sets of size k. Okay. And one conjecture that Mason made, I think, in the 70s, is that this sequence is log concave. So log concave. So what does that mean? That ik square. So at any k, the square of that is bigger than the product of the like the neighboring two. So this is sort of a strong form of unimodality. That's what one can think of. So in particular, really it comes from here. So if you take take independent coin tosses, n independent coin tosses, they might have different parameters. So independent Bernoulli tries, possibly with different parameters. And you look at the probability, like the probability of getting I, probability of getting 1, 2, 3, 4, 0 to n, all of this. And you write down the sequence. These sequences have the log concavity, ultra log concavity property. And this actually is equivalent to the so-called Newton inequality. So it goes back that far. So that's where and really, I mean, and then the Gaussian certainly is log concave. And so you can see that these things are sort of related. So this distribution sort of goes in the limit to the Gaussian ultra log concave. But anyway, so this log concavity sort of is sort of quite interesting form of unimodality in combinatorics, and this was a conjecture. And ultra log concavity, which is just that so that the same inequality holds with the quantity divided by the binomial, normalized by the binomial coefficient. That was also considered, and this is strictly stronger than that. That's just some algebra. That this ultra log concavity is always stronger than log concavity. And both of those, so this one was proven by Adiprasito and Katz in 2018 using this Chow ring thing that I said I wouldn't talk about. And that actually led to a flurry of lot of work, including the series of works by Anarai, Liu, Garan, and Vincent on the algorithmic sides of this. And now there are like three different, I mean, these two proofs are, this and this are, I think, somewhat similar. This one was somewhat maybe different, but yeah, there are three different write-ups at least you can find for proof of the ultra log concave, the stronger version of Mason's conjecture was all using roughly the strongly log concave and Lorenzian polynomial technology. Okay, here's another thing that that's very interesting that their theory does is something called closure properties. So this is one of the sources of power of the upper half plane stable polynomials, that they are closed under some very nice operations. So what kind of operations? So what operations will preserve that? So upper half plane stability is preserved under product is a trivial statement, or more or less. You can just easily check that two polynomials are upper half plane stable. The product is also upper half plane stable. But it's not so simple for these ones. In fact, Gurwitz in the same paper where he defined strongly log concave polynomials also wondered about whether they are preserved, whether the product of two strongly log concave polynomials is a strongly log concave polynomials. And one of the things that out of the several closure properties that this paper proves, one of them is that product does preserve this. And they actually sort of, to a large extent, are able to reproduce the much more complete theory for closure properties that happens for stable polynomials, but not completely. So there's a full calculation here. I don't think it's still there, but many of the operations do sort of carry over. In particular, one that I like and I don't have any use for it yet, but it's the following: that if f is Lorentzian, then the polynomial obtained by just deleting the non-multi-affine part. So anything where some variable has degree higher than 2, it's also Lorentzian. This might look like a curiosity. Why would one ever need it? But if you are if you're a connoisseur of these roots results, you might have heard of the Heilmann-Lieb theorem. It's an important theorem in the Liang theory. It's about the matching polynomial, and it says, among other things, that the matching polynomial is real rooted. There's almost a half-page proof of this statement, which using the map operation. So yes, it's a powerful operation, although it looks a bit strange. So it's the fact that the map of stable polynomials, so the multi-affine part of stable polynomials is stable, gives a very quick proof of that. So one could expect that multi-affine part of Lorenzian polynomials also has similar things. I don't know what yet, but Okay, so other success of the theory. So one, this is not what Juniha was involved in directly, but so here is another conjecture from computer science from the 80s, which is that more algorithmic. So you have a matroid, and one natural thing that you can now ask is how do you sample uniformly from the basis of a matroid? And one natural way to do it is to do a random walk on them. And one natural random walk is to, when you're a base, you have the exchange properties, you do a random exchange. How do you do a random exchange? You have a base, you choose a random element, delete it, and then try to add a random element that will still keep it a base. So that's the thing. And Mihail and Vazirani in the 80s conjectured that this walk is rapidly mixing. In fact, they conjectured a much more precise statement that the expansion of this graph is at least 1 in after suitable normalization. So this conjecture was fully resolved by Anari, Liu, Owiskran, and Winzen. And so, as you might, if you have been noticing the citations, you might have noticed that many of the same ideas were developed in these series of works also. So all of them were building upon the AHK, the Chowring papers that I'm not going to talk about, and also using ideas from. So this required also ideas from the work on high-dimensional expansion. And okay, so there are many aspects I couldn't cover, and couldn't here means a lot. I couldn't also because not just because there's 30 minutes here, but also because I don't know them. So as I said, many of the advances described here started with this paper of Adiprasita, Hugo, and Katz. There's also a nice sort of smaller survey they have in notices, I think, which is, so the paper is called Hodge Theory of Commutative Geometries, and the survey is called Hodge Theory of Matroids. Yeah, so I think they're the same, but anyway, so they have this. But this paper itself improved upon a breakthrough result of Juniha from 2012, which affirmatively, so it answered a conjecture of Reed, Rota, Heron, and Welch on something that I didn't talk about at all. So there's another polynomial you can associate with a matroid called the Capstick Polynomial. So that's a bit, the definition for general matroids might look a bit unmotivated, but for the graphic matroid, it's actually a pretty interesting object. It's a chromatic polynomial. So what's the chromatic polynomial? So you take a graph G of n, so fix the graph. There's a result that which says that there's a polynomial of degree equal to the number of vertices in the graph, so that when you put an integer q, positive integer q into it, it will give you the number of proper colorings of the graph. So proper colorings are assignments of colors. So q is the number of colors. You assign one color to each vertex in such a way that no two neighbors are the same color. So it's not immediately clear that it should be a polynomial, but actually the proof is quite easy. Once you start thinking about it, you just try to write a recursion and you get that it's a small degree polynomial. So this chromatic polynomial generalizes to something called to the Capstick polynomial from matroid. So Reed conjectured that the coefficients of the chromatic polynomial must be log concave. So it has alternating signs. So you remove the signs, and then they must be log concave. Rota, Heron, and Welch generalize the conjecture to all Capstick polynomials. Juniha proved it for, if I remember correctly, all representable matroids, and AHK proved it for all matroids. This log concavity. And so all of them, so this mixed volumes and a connection with something called mixed multiplicities of ideas, which I can only report as a name, was used in this paper. So the mixed volumes have a long history in this, and that's all.
So what's the significance for the chromatic polynomial log concavity of coefficients?
Yeah,
so I mean, how do you use it? I mean,
so commutatively, I don't think there is. Yeah, it's more about the structure of the chromatic polynomial. So, for example, so the chromatic polynomial is not real rooted. The matching polynomial, for example, is real rooted. Real rootedness implies ultra log concavity of the coefficients. So that's also Newton's inequalities. But so the question is, can you get to that without real root?
Okay. Any other question for Piyush?
It's probably much more a superficial question. So, like, since you mentioned about these things about having zeros in upper half plane, is there any connection with Liang theory of any of this?
Yeah. I mean, like, yes, in the sense that this is about. Yeah. I mean, in the sense that you were trying to characterize Liang-like results. Yeah. So, as I said, like the map operator gives you like a very short proof of this.
Okay, any more quick question? If not, let's thank Piyush once again. We can take a 5-minute break, after which Anish Ghosh will continue.
Hello, is it working? Is it working?
All right, so welcome back. So now, final speaker of the day, Anish Ghosh, will talk about the work of James Maynard.
Okay, so thank you very much for the opportunity. And I will repeat the disclaimers that all the speakers before me have given, which is that this is going to be a very small part of the work of James Maynard. So Maynard is an analytic number theorist. So in modern times, there seem to be two schools of thought about number theory. One is an algebraic approach to it, and one is an analytic approach to it. And Maynard is, I guess, one of the leading analytic number theorists today. And there's a folklore saying in mathematics, which is that modern mathematics tends to have extremely complicated sounding theorems. And, so the reason for this is quite simple. The reason is that there are plenty of very simple sounding statements which we have no idea how to prove. So what we do is we try to make statements more complicated and then prove them. So Maynard here is an exception to this rule. He goes after things which are very simple to state and manages to make new tools to prove them. So his work is characterized by two distinct features, in my opinion. First is he's very inventive, very innovative. But there are several cases, one of which I will present today, where things were stuck at some point and it was just sheer technical strength. He just ran through it, right? So it's a combination of both the things. He can produce radically new ideas, and he can also look at an existing problem stuck at roughly the same place for 50 years and just break through it. Okay, so that's what we're going to see. All right, so human beings, when they started counting with integers, the numbers 1, 2, 3, 4, and so on. And soon enough, we realized that the integers have some building blocks. Okay, so these building blocks are the atoms of the integers, namely the prime numbers. Okay, so we came to a rapid understanding that once we know enough about the prime numbers, we know enough about all integers. Okay, so here are the first few prime numbers, and all of us will agree that this list, these dots at the end of this list, are justified because this list goes on. I can keep on writing it, and I won't come to, at the end of the board, there won't be a biggest ever prime number because there's no such thing. Infinitely many prime numbers. Okay, so one can do a simple-minded kind of generalization of this and say, this list is quite interesting. In particular, it seems to have several prime numbers which differ by 2. Okay, so 5 and 7, 11 and 13, 17 and 19, and so on and so forth. So here's the list of prime numbers which differ by 2. Okay, so the first few are nice, and then I've put some dots and written some more complicated ones which I've copied from the internet. And now the question is, are the last few dots here justified? So is there a biggest pair of prime numbers which differ by 2 or not? Okay, this is a question which is very easy to pose. You can pose it to a middle school student, and a middle school student and a major number theorist would have roughly the same idea of how true it is. Nobody has absolutely no clue at all. Okay, no idea how to prove that there are infinitely many twin primes. Now, this is a sorry state of affairs, and this is the usual embarrassment of being a mathematician. You can't prove most things. But this story received a massive boost about a decade ago in what is, I think, one of the most romantic stories in recent times. And that story is the story of a mathematician called Yitang Zhang. Okay, So this is a breakthrough in which he proved, and this is really a technical conceptual breakthrough, in which he proved that, okay, I don't know if there are infinitely many twin primes, but I can prove to you that there are infinitely many primes, pairs of primes which differ by at most 70 million. Okay, so prior to this, there was no bound at all, no absolute bound. It was the first absolute bound. And I don't know if all of you have heard about this story, but if you haven't, please look it up. It's really a heartwarming story. So this is a mathematician, very, very strong, who did a PhD in algebraic geometry and then failed to get any kind of employment at all. And at some point, he was living in a car and working in a, as a delivery boy, and also in Subway sandwich shop, And then in his mid-50s, he came up with this amazing argument, which really changed everything, right? Completely changed the landscape of analytic number theory. So subsequent to this, all right, so there's one line in the middle about triplets of primes, but this is being ambitious. You can't even say something about pairs of primes and you want to go to triplets. It's simply out of the question. That's just for some entertainment. Okay, so after this breakthrough, there were several developments. So around the time that this was being proved, Maynard was a graduate student. He was finishing his PhD in Oxford. And this development really shook the world. Okay, so what transpired then was there was a so-called Polymath Project. This is some kind of thing which started in the mid-2000s and has now petered out, where people try to crowdsource proofs. Okay, so once you have an idea, get as many people on board and try to make rapid improvements to the proof. And so there was a big Polymath project led by Terry Tao. Separately, Tao was working on his own as well, and Maynard was working on his own. And Maynard and independently Tao produced a radical new idea which improved this very significantly. So, for example, here's two beautiful results of Maynard. So the first result improves this and brings it from 70 million to roughly 246. Okay, so this is, it might seem like it's true that 70 million, the first bound is really a massive thing, but bringing this down was also very, very difficult. New ideas were needed. The second result is a beautiful result, unrelated to this a priori, but ask the question, how can you find primes in sparse subsets of the integers? Right? So suppose I take the set of all integers which are missing a 7 in their decimal expansion. Would such a set contain a prime, 2 primes, 5 primes, 10 primes? And Maynard proved a beautiful result that there are infinitely many primes whose decimal representation, base 10 representation, does not contain the digit 7. So to give you some idea of the difficulty in this, if you try to remove 2 digits, it's still not known. So if you say, okay, what about 7 and 8 together? No idea, right? So it's really kind of a very impressive achievement. And these results and a lot of Maynard's work, they rely on 2 things. So one is what is called a sieving method. And the second is what is called the Hardy-Littlewood circle method. So this is some kind of very classical tool in analytic number theory, which in this result, this digit 7 result, Maynard has pushed to a level which was probably not expected. Okay, so these are his results on prime patterns, and there are many of them. And these are part of his citation for the Fields Medal. But he's also done some remarkable work in a slightly different area, which I'm now going to describe. Okay, So there's a very old conjecture in Diophantine approximation. I say conjecture, but it's no longer a conjecture. It was until Koukouloupoulous and Maynard came and resolved it 2 years ago. So this is something called the Duffin-Shaffer conjecture. And for the rest of my talk, I'll try to explain what this is and why solving it was a very impressive piece of work. So, you know, as a species, we learned to count and then we learned how to multiply and divide. And so we had at our disposal integers and rational numbers. And then, you know, mostly because of practical reasons, we learned about irrational numbers. Okay. And so in school, if someone asks a kid what is pi, you know, there'll be one kid who'll say 22/7. There'll be one kid who'll say 3.14. There'll always be one oversmart kid who knows like 15, you know, digits in the decimal expansion of pi, or one who knows 50 or 60. And so what does this mean, right? So this means that pi is a complicated, mysterious number. And what we should try to do is understand it through better and better rational approximations. Okay. I know how to count things which are discrete and take ratios, not much more than that. So what I should try to do when faced with a number like pi is try to get better and better at viewing it as ratios. Okay, so which ratios are the best ones to understand pi? This is the subject of Diophantine approximation, goes back thousands of years. And it also has the same problem as the theory of prime numbers does, which is that even the most basic questions are completely out of reach. Okay, so for example, if instead of looking at decimal expansions of real numbers, you use what is called a continued fraction expansion, then you come to the following theorem, which is attributed to Dirichlet, but was probably known before him, that given any irrational number, you can find infinitely many good rational approximations to it, where the good is quantitatively measured in terms of the square of the denominator. Okay, so in other words, like in the case of pi, there are many rational numbers which seem to be not very far from pi. I'm going to measure how good an approximation it is by trying to measure it using, excuse me, by trying to employ the denominator as a measure of complexity for the approximation. Okay, and so this is something which is easy to prove, and it's a very comforting fact that all is not lost. Given any irrational number, I can at least do this. Okay, so this is fine. All right. On the other hand, it's really very hard to figure out properties of individual numbers like pi, or, you know, almost any number that you give me. It's very hard for me to tell you precisely what kind of Diophantine properties it has. For example, given the fact from the previous slide that every real number has good rational approximations with denominator squared, you could define a notion of Diophantine complexity by asking how much this square can be improved. Okay, what's the extent to which it can be improved? And so this quantity is called the exponent of this number. So Klaus Roth, in an important work which was partly responsible for him getting the Fields Medal, proved that algebraic numbers always have 2 as this number. Okay, so if it's an algebraic number, if it solves a polynomial with a degree 2 polynomial with integer coefficients, then it has no choice but to have 2 as its irrationality. Okay, but that's really a great result. On the other hand, nobody has any idea what the irrationality exponent of pi is, simply out of reach. So this very unsatisfactory state of affairs led mathematicians to look for a way out. And a way out, a profitable way out, is to ask yourself, can I say something probabilistically? Okay, so I don't know what pi is in terms of irrationality exponent. So let me close my eyes and pick a number at random. Maybe I can say something better with probability 1, right? So you're sacrificing a deterministic answer, but you hope to gain in terms of precision of the answer. So almost surely you hope to gain much more. This is the hope. And so this led to the birth of probabilistic number theory, where this result of Kokolopoulos and Maynard is situated. Okay. So another problem which is a little bit on the esoteric side, I mean academic side, but something which certainly I would enjoy is, in this approximation here, you're allowing all sorts of rational numbers, okay? And so just out of curiosity, you could ask, well, can I approximate this number with many rational numbers whose denominators are prime numbers, right? So what I'm doing is I'm taking a large set of natural numbers and removing a sparse set and demanding that my denominators come from this sparse set. And the question is, can you still do that? Okay, so sampling denominators in sparse sets. So here's a relatively recent and powerful theorem of Matomaki, which says that you can actually do that for any rational number. You can solve this inequality in rationals, so denominator is a prime with an exponent of -4/3. Okay, and we still don't know what the right answer is. It's supposed to be 2, not -4/3. So this kind of question, right, is exactly what I was getting at. It's a very powerful theorem, but it seems to be off. It's not the right answer. So the question is, can you sacrifice every irrational number by saying with probability 1, but get the right answer, right? That's the question. Okay, so this is the kind of perspective that's very widely prevalent these days, and it's a very kind of powerful perspective, which is that often it's much better to look at arithmetic objects from a probabilistic point of view and try to prove that enough objects in this space have the right Diophantine properties. So for reasons which are not entirely clear to me, this area is called metric Diophantine approximation. I think it has something to do with the Russian origins of the theory and something being lost in translation. But in any case, it's a probabilistic point of view in number theory. Okay? So let's try to really get a very concrete answer now. So what we're going to do is, I'm going to take the same inequality, x minus a over q, and replace the denominator squared or the denominator to power by an error function. Okay, an error function. So this generality has an advantage. It encompasses all the other examples I've spoken about. For example, this function could be supported only on the prime numbers. That would give only prime denominators, and so on and so forth. And so the question now is, can you obtain a satisfactory answer as to what size this set A should have? Okay. And of course, you might say, okay, this is too vague a question. It should depend on something to do with this function and so on and so forth. Maybe it's too ambitious. So it turns out that there was a beautiful theorem of Khinchin from the 1920s. And this theorem says that, in fact, there's a very clean dependence of the size of this set or the probability of this event occurring with regard to this function. Namely, almost surely you won't be able to solve this inequality infinitely often if this sum converges. Okay, so this is the first part of the theorem. The second part of the theorem says that if the sum, on the other hand, if it diverges and something else happens, so some complicated thing about this function happens, then almost surely you do in fact get infinitely many solutions. Okay, so this is the theorem. It's a very nice theorem. Those of us who have had some probability will recognize in this theorem the Borel-Cantelli lemma. Okay, so this is a standard theorem in probability, and it says that whenever you have such a situation where you want some event to happen infinitely often, then what you need to do is simply check if the sum of the measures of the sets involved converges or not. If it converges, then the set of points which belong to infinitely many of these sets has zero measure. So it's very unlikely to happen. With probability 1, it won't happen. On the other hand, if the sum diverges of measures, then you're not quite there yet, because you need an additional condition. You need something called pairwise independence. So if the events that you have in mind depend on each other, then you're not going to get the conclusion that this event happens with probability 1. You have to have some independence. Okay, so this is a very standard theorem. And roughly, if you correlate the two parts of this theorem with the previous slide, you see that they kind of match up. Okay, so there's something converging in the first one and something converging there, and vice versa. And then you can kind of tell yourself, maybe, there was some pairwise independence there, and there's some other condition here. Maybe they're related to each other. Okay, so I don't have too much time, so I'll maybe get straight to the problem. Okay, so this is a slide which I just explained what I said, that these two theorems kind of match up. Okay, so there's a slide which I'll come back to. Let me first state the problem. So the problem is the following. So in the second result that I stated, it said that with probability 1, something nice happens, provided two things happen. One, sum has to diverge, and some function has to decrease. Okay. So now the issue was that some function decreasing was seen to be unnecessary. All right. So this was a condition. This condition is a very restrictive condition. For example, it doesn't allow me to sample denominators in the primes, because if I want my function to be supported on the primes, I can't have it to be monotonically decreasing. Right? So dropping this condition would mean that I have a lot of freedom at my disposal in terms of how to arrange approximations for this number. Okay, so I'll just go back one slide to say that due to work of many people, including Professor Dani here, this kind of question has a geometric interpretation in terms of geodesic flows on the modular surface. So if you take the quotient of the upper half plane by a lattice, you get a nice finite volume surface, and this kind of question admits interpretations in terms of that. And so what we're asking now is, from an ergodic perspective, it's kind of a difficult question. We're asking, there's some chaotic flow on this modular surface. Can you sample it at essentially any sparse subset of times that you want and still get some good result? So it's a very, very hard question. Okay. So it turns out that you can't immediately drop it. You can't immediately drop this condition. There was an explicit example given by Duffin and Shaffer in 1941. And there's essentially only one problem. And this problem is a problem which has to do with dependencies among the denominators. So what they proposed was a simple fix. They said, let's not try to approximate it with all possible denominators, but let's insist that the numerator and the denominator have GCD 1. That's it. No other condition needed. And so there was a kind of refined conjecture in 1941 by Duffin and Shaffer, which said that if you insist that these fractions are reduced, then you should have a clean statement. So this clean statement has no conditions about something decreasing, increasing, nothing. It's a clean statement with one small difference, that we have Euler's phi function over here. And that's because that's the number of integers below a number with GCD 1, right? So it's going to show up in the count. That's all. So this was basically the conjecture, and there was a lot of work done by various people, by Erdős, by Dyson, and Castles, and so on and so forth, including a lot of work recently. But finally, in 2019 or 2020, I guess, it was a spectacular progress. Maynard and Koukoulopoulos and Maynard completely settled it. So I don't have any time to explain how they did it, but basically, let me just kind of explain one thing, which is that it's sort of a so this independence is the main issue. Somehow these events are really not independent, and it's not that you can't prove they're not independent. They're simply not independent. Okay, it's just it's not a lack of ideas. It's just a fact that they're not independent. So essentially, what you have to do is work very hard and kind of isolate these dependencies. And so there's some complicated thing, and you've left with some exponential sum. And this was the state of affairs for about 25 years. You're stuck at this sum. Don't know how to estimate the sum. So what people were doing is giving themselves a little bit of room. Maybe I add one more condition and something happens, one more less condition, this and that. So Koukoulopoulos and Maynard had a beautiful idea, which is they converted this to a problem in graph theory. So they created an object called a GCD graph. And this idea goes back to Freeman-Dyson. And so there's some technology called which they call an iterative compression algorithm. And they created the beautiful strategy. So they have a graph where the vertices are integers, and the edges kind of tell you the dependencies among the GCDs of these pair of integers. And so they have a compressive iterative algorithm which kind of takes a fairly large bipartite graph, at each stage reduces it to a subgraph and keeps on reducing till you're left with something which essentially has a very clean structure. You know exactly what the dependencies are. So you can try to estimate this on some limit graph, and then kind of work your way up from there. I'm out of time, so I'll stop here. Thank you.
Questions?
So with this estimate, is it like like second moment, some kind of analysis?
Yes, the second moment analysis, absolutely.
Because it basically relate the intersection probability to the product of these
That's
things,
right,
and
that's
by
right.
then
Yes.
you can control.
Absolutely.
Okay.
So this is a question about something in your early slide.
Yes.
So this is about there's infinitely many things without digit 7.
Yes.
Is there a version of the prime number theorem within those things? I mean, is he actually explicitly computing asymptotics, or
No, he has explicit asymptotic. Yeah.
Oh.
So the number of primes with digit without 7 as a ratio of all primes is the number that you'd expect.
I see. And presumably 7 there's nothing special about 7.
Nothing special about 7. Yes. I should have mentioned that. There's nothing special about 7.
Yeah. And is there any, is he using some mixing results for this, or?
So
because your next statement that if you drop 2 digits, nothing is known.
Yeah. So basically this thing is kind of also, so, all previous attacks use the Hardy-Littlewood circle method. But there was some barrier which he has broken. So there's some barrier. Now the barrier has to do with symmetry in the problem. So previous results of this kind has some natural symmetry which was exploited. This one doesn't have it. What he does use, and I don't understand it properly, is he uses some Markov chain argument. At some point, there's some. It's a really tour de force. I mean, it breaks down as some. There's a barrier. He breaks it down, and then he uses essentially whatever is available: geometry of numbers, probability, Markov chains, random walks. Everything somehow comes together and finishes it off.
I didn't say this last part when you said GCD1, that's for A by Q.
So A and Q are co-prime.
Okay. So, I mean, I thought when you were writing this, before you said that,
Yes.
I mean, that's automatically assumed because when you were trying to write something.
Right. No, it wasn't assumed in the initial problem because, in the initial problem, I was just trying to take a irrational number and approximate it using infinitely many rational numbers. I was allowing dependencies in the numerator and denominator. I could have done the same thing from the beginning and just added a phi function to the summation.
So most of these convergence properties will become much worse if you just multiply numerator and denominator by 1 million, right? So
that's true, but that's the thing is that that's one of the things. So we are essentially looking at a very soft probabilistic state. So the statement is that almost surely there are infinitely many solutions to this thing. Yes. In any concrete situation, of course, I would like to avoid. I should say that many of his results are unconditional. Everything is unconditional, and it doesn't help in these things to assume, for example, the Riemann hypothesis. It really makes no difference.
Any other question?
This actually, I always wanted to ask an expert actually, since you said like when you came across this romantic story. So how different were Maynard's and Itang Zhang's proof? Like they're very different, like?
No, so basically there was a breakthrough work of Goldstone. I forget the pronunciation of the last other two names. So let me not embarrass myself and say Goldstone and co-authors. So this was a breakthrough work which kind of around the early 2000s, which didn't produce an absolute bound like 70,000, but got it into some range, right? And so both Zhang and Maynard and Tao have improvements to. So basically, somehow they were using some technology, and that technology needed some bounds. So there was a Friedlander-Ivanich technology. They needed some very good way of solving this Goldstone type problem. And so conceptually, I guess there's kind of, no, I wouldn't say that. I mean, there's really some new stuff going on. Basically, what Maynard did was find a way of pushing this Goldstone type thing much further so that he satisfies the hypothesis assumed in this. So this, conditionally, so conditionally on various other things, now you can bring it down to 7 or whatever. 2 seems to be kind of very difficult. So this, it's probably vastly clear by now. I'm not the right person to ask very fine questions on this particular thing, because it's sort of. So I should say that, if you go back around 20 years or something, then the subject was sort of very sluggish. And then in the last 20 years, there's been like an explosion of activity. So now they're like, very, very powerful analytic number theorists scattered everywhere, continuously working on this stuff. So as I speak, some student somewhere might be proving this thing. You never yet know.
All right. So if there are no further questions, let's thank Anish again. Also, a big round of applause to all the pipe